So thank you for this very nice invitation, and I'm pleased to participate to this web seminar. So we discover this new way to share results and to share science during these last 2 years. I think it's great because we can meet more times and share more times, and for the environmental impact, it's quite well, of course. But I really think that we also need to meet at some point face by face to discuss and to know better each other and to continue to have colleagues and friends around the world. And that part of the job also, I think that it's a great part and a great phase. But so today, so today I would like only to have a simple slide here to remember all of you that we really need efficient catalysts for H2 production. When I start to work on that, as my background, I was more interested in to develop functional and structural models for enzyme in the field of small molecule activation, because I really like to understand the mechanism, and so I was more on the fundamental side. But it's true that in last years, I really realized that it's nice to understand, it's nice to develop models and things like that. But at the end, we really need to go maybe, or to try to go a little step further because there is a real need, and a real need because H2, of course, is known to be a very interesting energy vector. But in chemistry also, what we see is that we also need H2 for a lot of different types of chemistry. Like, of course, CO2 reduction is a big field. We will not talk about that today, but some people try to use CO2 to close the carbon cycle. But at the end, a solution, and a nice solution, will be to react CO2 with H2. And in that case, we really need to have H2 in a big volume and at low cost, and in a very green condition. And it's exactly the same for N2 if we want to do ammoniac. So I really think that the question of H2 is not only for H2, but it's also come in a more global system, that we really need H2 to do a lot of things, and not only as an energy vector. And so, so today I will focus more on what I like, on models and bio-inspired models, and see how, as chemists, we can help to understand all this mechanism. But also at the end, I would like to show how we can also try to improve our system, and maybe to dream to that they can go for some application in the future. So a very short slide, because I'm sure that you all know very well the nickel iron hydrogenase. This enzyme, of course, the Grenoble people like it because the structure was resolved by Juan Fontecilla and his team in Grenoble. And it was very surprising for everyone, I think, because it was one of the first organometallic complex inside a metal enzyme with a iron carbon bond in the active site. So I think we all agree now with the mechanism that I show here, that was proposed by Kai Vincent a few years ago. And if I go through the production of H2, I remember very quickly that first, of course, you start with this nickel 2 iron 2 compound that you reduce first in this nickel 1 iron 2, which can be it can be, I don't know what, something up. I'm sorry, but I have a problem with the. Okay. To the formation of this first hydride species, a nickel 3 iron 2 hydride species, which can be reduced to a nickel 2 iron 2 hydride species, and with another protonation, you can release H2. So what it was very important for me when I start to work on the modeling of this enzyme is that all the redox chemistry occurs on the nickel side, from nickel 1, nickel 2 and nickel 3. And that was quite surprising for me, because nickel is known, of course, and is capable to stabilize this kind of oxidation state. But normally iron is also well known to do all these different oxidation state, and apparently it was staying at this iron 2 state. So that was something that was very interesting me, and also, of course, all this sialate, this very rich sialate environment. And if you look at the literature, of course, when people have seen this very nice active site, Darensbourg was the first to propose a structural model of this enzyme in '96, and but it takes like around 10 years to stabilize a dinuclear compound that really feature all the different important structure of this active site. But this compound, even if it was very important to be able to isolate and characterize the species, it was very unstable, and no reactivity at all have been described with that. And then you have many people and big group like Ogo, Rochefous, Lubitz, and Artero group who describe structural and functional models, and also were very interesting in stabilizing hydride species and very important intermediate species. When we start to work on this enzyme, so what we wanted really is to put all the reactivity on the nickel side, and it was not the case with the previous models, mainly. And in the lab, we have been able to isolate this mononuclear nickel 2 complex that was capable to be stable at different oxidation states from nickel 1 to nickel 3. So we thought that it will be a good thing to synthesize a dimer using this brick. And as you can see here, we were able to isolate and characterize this nickel 2 iron 2 compound, which feature very comparable structure from the enzyme. This compound has very interesting redox activity, because we can stabilize it into 2 different reduction state, nickel 1 iron 2, and a second reduction occurs more on the ligand. That have been shown by different spectroscopic technique and theory, but it was very important for us to see that these 2 systems were very quite quasi-reversible, so meaning that normally they should be quite stable and could be directly involved in the catalytic system. So from this system, of course, we try and see that this complex was a very good electrocatalyst. So we were able to see that here when we add some protons into an acetonitrile solution, we can see the development of the catalytic wave, and also we were able to measure the formation of H2 during an electrolysis. Moreover, when we compare the reactivity of this compound in black here, in red here, sorry, you can see that it was a very good compound, and for a bio-inspired complex, it displayed very good reactivity. So we were very happy with that, but as I said before, I was more interested at that time in mechanism, and so what we try to do is really to try to isolate intermediate species, and for that, of course, you need to use a lot of different spectroscopic techniques, and it was exactly what we do. So we start from the compound here that we fully characterize, and we were able to isolate the first 1 electron reduced species, a nickel 1 iron 2 compound. So we use infrared spectroscopy to follow the CO here, and we have seen that from the shift of the CO vibration that it was bridged between the nickel and the iron 2. From the EPR, it's clear that the signature, and it was confirmed by DFT, that it was more the signature of a nickel 1 compound than iron 2 compound. And from the mouse borer, we have seen that the signature of the iron site was very similar to that from the initial compound. So confirming that the reduction occurs on the nickel site. So with that, we also were able to observe a very short-lived and very unstable species, this hydride species, this nickel 2 hydride iron 2 compound. The hydride being bridging between the nickel and the iron, but more close to the iron and not to the nickel, like in the enzyme. And we were able to observe it by infrared and by NMR, but it is very, the calculations, the DFT calculations that Michael performed on this compound that fully give us the solution and to show and to give us the good signal, the good photo, I would say, and structure of this compound. So then what we have observed is that we know that certainly we go through this way, so that we need to reduce 2 times the complex before to react with proton, and that this hydride species should be reduced and protonated again to release H2. And if we want to very follow the mechanism proposed for the enzyme, what we should is that we should react directly this nickel 1 iron 2 compound with proton. So for that, what we decided to do is to use a stronger acid. Of course, it's not that easy, because when you use stronger acid in such a condition, you are always afraid that you will kill your compound and that you will break your compound in 2 parts. It's clear that we cannot use so huge concentration of acid, otherwise the compound is not stable. But with HbF4, we have seen that we are capable of producing H2 clearly with a very good efficiency, and that at that time we really turn on the first reduction system, so meaning that the mechanism should be closed from that of the enzyme. But more importantly, in parallel, we decided to see if we can work in water. And to work in water, we decided, because the complex was absolutely not soluble in water, so the only way, if you want to go to water, and here, of course, it was also the idea to say, okay, we have a good compound, it works, we have an idea of the mechanism, and now what next? So what next is to try to improve the efficiency and the interest also of this complex. And so for that, we decided to immobilize the compound on the surface, and that was where we start to collaborate with Abhishek Dey in Kolkata. And so the complex was immobilized on graphite, and with this modified electrode, we did some different electrochemical experiment. And as you can see here, when you decrease the pH, you can see the appearance of this huge decrease in the intensity, telling you that something happened. And when we did a bulk electrolysis at -0.1 volt versus silver at pH 3, we have seen the formation of a lot of H2 without degradation of the surface of the electrode. So meaning that after 10 hours, when we look at the electrode before and after the electrolysis, we have observed quite exactly the same signature, meaning that the compound is still able to continue and to go on. So you have seen that it was efficient with a lot of turnover number, a lot of H2 produced, and very rapid. Moreover, what was interesting here is that we have seen there that the complex can follow, at least during the 2 first steps, can follow the same reactivities as the enzyme. Of course, you know also very well also the hydrogenase, the iron hydrogenase. And when I look at both compounds, you can see a lot of different similarities between these two complexes. Of course, there are two organometallic compounds with CO with CO ligand, and what you also observe is that it's very sulfur-rich environment. Very important maybe difference in this iron-iron system is that you have a iron-sulfur cluster directly linked to the dinuclear iron compound. So what we wanted to see if is how can we look at the impact of the nature of the metal on this compound. And so what we try to, when I start to do that, I look at the literature to see if some people already try to compare exactly isostructural compound where they only exchange the one iron or one nickel by each other. And so I found two series, I will call them like that. So this iron one compound, and you can see here that you have also the iron 1 nickel 1 compound, but unfortunately when one is active and the other one is not active, so it was very hard to compare the reactivity in that case, of course. And the second example, sorry for the mistakes here, and for the second series was this one, but both compounds are active, so it's fine, but it's not that so good to if you directly compare a nickel 2 with the iron NO compound. It's not exactly the same electronic structure, so it's not a clear comparison. So we try our best with this system to synthesize exactly the same complex where only the nickel was replaced by an iron. So to do the synthesis, we start from these dimers where you have two iron 2 with the ligand, the ligand that we wanted to have on the iron side, on this side. So we made a lot of crystals in a lot of different conditions, but we always finish with the same structure with 2 CO on the compound. So we were quite, of course, disappointed, because what we wanted is really to have only 1 CO on this side, on the CP side, but not on this side. But when we look at the spectroscopic properties of this compound in solution, we were surprised to see that it was not that simple. And that, for instance, that here you have the powder, so you see the 2 CO vibration coming from these 2 CO, and in dichloromethane it was exactly the same, so you can clearly see the signature of these 2 CO. And then when you go to in acetonitrile, and depending the concentration of the acetonitrile, what we observe is that we have another compound, and it was clear that some equilibrium was going on here, that something was going on. So I will make the story short, but I can tell you that it took us some time to really understand everything. So what we observe by UV here is that when you start in blue, you put the compound, so you have the infrared here. So you have a mixture between two compounds, and when you add CO, you see that you form another species, which has exactly the same infrared than in dichloromethane. And when you start from this compound with CO and you pump the solution, you bubble nitrogen inside, what you see is that you form another compound, the pink one, and now you have only 1 CO vibration. So it was clear here that we have an equilibrium between a form with 2 CO and 1 CO. But the good point is that we are capable now to form a compound with only 1 CO. Which I show you here, but you will say that it's not exactly the same, but at the end, the CO was, by DFT calculation, it was shown that the CO are more close than to this iron side. So we were quite close to the nickel iron compound. So when we look at the reactivity and first at the redox properties of this compound, you can see here that we have two redox systems, which are also reversible. So that was very nice. We try again to isolate the first one electron reduced species. And in that case, it was not exactly the same electronic structure than the nickel and iron compound, because in the nickel iron, the reduction occurs on the nickel. And here what we observe is that we finish with a mixed valence species, which is called class 2 delocalized, because as a function of the temperature, you have a delocalization, and then you have the localization on only one iron, depending the temperature. But from DFT calculation, we were quite surprised to see that the CO now is not anymore on the iron with the CP, but on the iron with the N2S2 ligand. The compound is also active for H2 production, and clearly here, only from looking at the CV in the presence of a small amount of acid, here only one equivalent in red, we have seen that we can follow the mechanism and see that we need to reduce 2 times the compound before to have its protonation, and then the protonated species can be reduced again at this potential at minus 1.84 and react with another proton to release H2. So here in that case, because the potential was a little bit different, we clearly see from the CV the mechanism, which is quite comparable to that was observed with the nickel iron compound. Again, what we try next to do is to immobilize the complex and to see if we can have a good compound. And as you can see, so we are capable to compare the 1 CO compound to the 2 CO compound, because depending the concentration of the solutions that we use to immobilize the compound, we can isolate both compounds. And we have seen that the 2 CO compound is more interesting, of course, because it tries the potential, and we again have a very efficient system, but a little bit less than the nickel iron compound. I will finish with that. It was a very surprise result that we obtained quite recently. So we did exactly the same compound with cobalt, because we knew that the cobalt in that field is quite used for the Eminix system, for instance, to do this kind of catalyst. So we say, okay, we will try to see if a cobalt iron compound will be more efficient. So again, we have isolated the cobalt 2 iron 2 compound and also the cobalt 1 iron 2 system, characterized by infrared and EPR. So EPR, of course, it's this cobalt 2 iron 2 compound is spin 1/2, and this cobalt 1 iron 2 is spin 0, so no more EPR. What we have seen is that from the redox chemistry of the compound, it was very promising, because you see that the first reduction process occurs at minus 1 volt. So we were very interesting from this compound, and say, so maybe it's promising. And also you see that the second reduction occurs the nickel 2 iron 2 complex. But unfortunately, when we look at the reactivity of this compound with the same acid as before, there are quite no difference between the blank if you add the compound, the complex or not. So this is something that we still do not really understand, why there is really no reactivity of this cobalt complex compared to the nickel and iron. Clearly, the replacement by nickel and iron has not so strong impact on the reactivity of this type of compound. And it's certainly due to, because everything is quite, because the ligand is not innocent. And when you use acid like we use, not strong acid, it's clear that we need to reduce 2 times the complex before to be protonated. And when you reduce 2 times the complex, all the reduction, the secondary reduction occurs on the ligand. But clearly it doesn't explain why the cobalt compound is not that reactive. So I will finish here. I will thank my collaborators, Marcello Gennari and Vincent, with who we developed all this compound. Also Professor Abhishek Dey, who was who is of great help to do all, to start with this project with the heterogenization. And my friend Frank Meyer for the MOSPOR spectroscopy, Maëlys Sorio for the calculation, and Michael, and also the 2 PhD students who work on that and who have finished now, Deborah Brazzolotto and Yankee Wang. And I want to finish very shortly to tell you that you have still time to submit your abstract, because we will be very pleased to welcome all of you to Aerobic at Grenoble next July. 62 slots are available for communication, a selected communication. We made some invitation, of course, but we really wanted to give the opportunity to the maximum of people to propose an abstract. And so 62 slots available. So don't hesitate if you want to submit an abstract, you will be welcome. So I will, yes, so I'm finished, and thank you for your attention.
Thank you very